All right, variation functions. This is probably going to be the easiest lesson for you in this unit, probably. We're kind of going back to middle school or Algebra 1 concept a little bit and doing some stuff that we did a while back. I'll show you in the first thing why this is in this unit. But the math itself is actually really straightforward. So let's dive in. So there are two main types of variation functions. There is a direct variation function, and there's an inverse variation function. Now, the reason why this unit, excuse me, the reason why this is in this unit is because inverse variation is it can make a rational function, right? Because it or a reciprocal function, I guess, because it doesn't have all the extra bits. But that's also a rational function, just a more specific kind. And so because this x is in the denominator, and so that's why this is in this unit. So the two patterns that we're looking for are varies directly and varies inversely, and the k is the same in both of them, and it's called the constant of variation. Now, when you learned this topic before, because you almost certainly learned direct variation before. You've almost certainly seen it. You may not remember or whatever else, but you almost certainly have learned that before, either in pre-algebra or algebra 1 or both. And so you've probably seen this before, right? And you may have solved it with proportions before, and you can certainly do that. The book that we're using in my classes at the moment, they set up a proportion for all of these problem types, and I debated back and forth with myself on whether I wanted to teach it that way or teach it the way that I have typically done in the past. And I'm going to agree with past Sean, and I'm not going to teach it that way. And the reason is because I think it can get confusing when we start getting compound variations, and we have joint variations and some of these other things that aren't really that confusing. And it's not that bad to put it into a proportion. If you want to look, if you're one of my students, you want to look at the book and how they do it, or if you've done it that way in the past or whatever, that's totally fine. Do it that way. But I just wanted to. I'm not going to do it that way. I'm going to teach it in a straightforward pattern that gives us a function, and then we use the function to do. It's more of a physicsy way of doing things, or an engineering way of doing things, where we kind of have set up our formula and then we use that as a tool later. So let's dive into some examples. It's not. I'm kind of probably sounding a little bit scary. It's not that bad. I don't want it to confuse somebody if they're like, "Oh yeah, I just set up a proportion." You can do that, and if you do it that way, you'll get the same answer, and it's fine, not a problem at all. So, y varies directly as x, and y excuse me, y equals 15 when x equals -5. So what we're going to do, kind of the method to the madness, is we're going to figure out which formula we're going to use. So it says varies directly, so we're going to use a formula y equals kx, because that's varies directly. Y varies directly, it goes in a direct line to the x, right? And then you'll kind of, once you identify your formula, you'll solve these problems, all of them basically in kind of two phases, where we'll get the equation, then we'll get the k basically, and then we'll which will give us the equation, and then we plug some other numbers in. So now for the next bit. So y equals 15 when x equals -5. So we're going to plug those numbers in here to find k. So into y, we're going to put 15 equals k times x is -5. Then to find k, you just divide both sides by -5. So k equals -3, right? So our formula then is y equals -3x, right? Little linear function. I said that the direct variation ones make nice linear functions, and that's probably where you learned about it. And then we're going to find y when x equals 7. So we're going to do exactly what you probably figured we do. We're just going to say y equals -3 times 7. And so y equals -21. Now, again, why am I saying this is a more engineering kind of way to do it, physicsy way to kind of do it? Because we're setting up our equation. This is how the situation works. So we could do this first half, and we could chunk off this whole ending bit of this question, and we could find y when x is whatever, right? And then, or X when Y is whatever. And so if you do it just with a proportion, you kind of are setting up a new problem every time. This is kind of getting you a better setup. So I think this is probably more applicable to more things, and it's a little less confusing kind of for some math students if we do it this way, because it's less different things. There's only kind of two different things. All right. Another example, if y varies inversely as b and a equals 28 when b equals -2, find a when b equals -10. So which one of the two formats are we going to use? We're going to use y varies inversely, so k over x. And then, except these are not. A varies inversely as b, right? So now we'll plug in 28 in here and -2 in there and solve for k. So a is 28 equals k over -2. How do we get rid of this -2? It's divided, so we multiply both sides by -2. So k equals 56. So our equation is a equals 56 divided by b. Right? So how are we going to solve for that? Well, we multiply b on both sides, and then, oh no, just kidding. We're not even there yet. Sorry, I've been debating so long about all this that my brain is all scrambled. So find a when b equals -10. So we're going to put a -10 in there. So a equals 56 divided by -10. So a, in fact, equals -5.6. Easy peasy, lemon squeezy. Did you spot the mistake? Because I made a mistake. -2 times 28 is -56, which means this would be negative, which would mean our answer is positive 5.6, or 5 2/5 if you want to write it with fractions. Okay? Easy money, right? What about if it says varies jointly, right? So varies jointly means this would be y. Oops, I didn't write that in. Let's write it now. We would read this sentence as y varies. Varies jointly as x and z. Or Z if you prefer. Okay, so it's just like a double direct variation, right? Just it varies directly as both of those things. I didn't, again, in my scatteredness, trying to think about method, I forgot to say kind of a conceptual idea. There's a lot of kind of concepts, a lot of just words in this video, apparently. It's still going to end up being not too long one, I think. But what the situation looks like is when x goes up, y goes up, right? Y gets bigger. With an inverse variation, as x gets bigger, y gets smaller, and vice versa. So they're going up together. As the one goes up, the other one goes up. And on the inverse, as one gets bigger, the other one gets smaller, or vice versa. That's what's happening. So back to this joint variation. As either one of these goes up, y goes up, right? All the things. As y goes down, at least one of these goes down, right? All of that. But that's more just like ideas planted in your brains for future use of these ideas conceptually in other classes. Suppose y varies jointly as x and z. Find y when all the other words. So I'm going to stop here. Y varies jointly as x and z. So what format are we using? The one we just learned, obviously. Y varies jointly as x and z. Find y when x equals 9 and z equals 2. Now this one's kind of tricking you, right? Because typically on or previously in our first two examples, the first set of numbers was the ones we plugged in first. But in this particular one, we're finding that it kind of puts the cart before the horse here, right? Because this is the one that's complete and has all three of the numbers, and this is the one we're finding things. So we're actually going to start by plugging in these three numbers to find k. So we're going to put 20 where the y is, k, and then times, and then 5 where the x is, and 3 where the z is, Multiply those, so 20 equals k 15k. Divide both sides by 15. K would equal, that'd be 10, no, not 10. That'd be, sorry, brain break, 4/3. So 4/3. That's what we're trying to say, right? Let me pause. I don't know. My brain's broken. Yeah, it is 4/3. I don't know. So k equals 4/3. Now, if you got the decimal out, I wanted to leave that as a fraction, and I want to leave it as a fraction because if I get the decimal one, then we're going to end up with 1.333 repeating, and so we're losing accuracy if we just put in like 1.3 into a calculator or something, or did it by hand or whatever. So we're going to keep that as a fraction to keep our accuracy in there. So our equation is y equals 4/3 xz. So find y when x equals 9 and z equals 2. So y would equal 4/3 times 9 would be 4 times 3, which is 12, times 2 is 24. You can check it on the calculator yourself if you want to. All right. Combined variation. What if we shove stuff together? Last example here. Oops, we don't want all that there. So, what if we stick stuff together? It's just as easy, actually, as what we did before, and we're just going to kind of read it straightforwardly through. So, suppose f varies directly as g and varies inversely as h. So, f varies directly as g, so k times g, and inversely as h. Now, you might be like, well, does the fraction go underneath the g or the h? Well, remember that, like, if I multiply 1/2 times 3, then I would put the 3 over the 1, and so the top is on the top and the bottom is on the bottom no matter what. So, I'm going to write the fraction bar across the whole thing, but it really doesn't matter is the gist of what I'm telling you there, right? So there's our formula. There's our setup. Find g when f equals 18, h equals -3. So this also, like the last example, kind of puts the cart before the horse, right? Because it's got the find the thing first and then the part with all of the things second. So we're going to use these last 3 numbers in here to figure out what k is. So g equals 24. Okay, I could write 24k if I wanted to, right? H equals 2, equals 2 equals 6. So I can multiply 2 on both sides and then divide by 24, or I could just divide by 2 first. I think I'm just going to divide by 2 first. 24 divided by 2 is 12. Oops. You could do it either way. K equals, no. 24 divided by 2 is 12. That's what I'm trying to say. And then, I don't know what's going on there. Divide both sides by 12, and we end up with k equals 1/2. Now, this one, we could change to a decimal if we wanted. We wouldn't be losing, it's not a repeated thing or anything. We wouldn't lose any accuracy, but I'm going to leave it as 1/2. Okay, so we want to find g. So f equals 18. So this is also a little tricky where it gives us the number that's the isolated number. The blank varies blanketly like the blankety blank. It gives us that first blankety blank blank, right? But we're going to do it just as easy as everything. Now we've got a fraction and a fraction. Nah, don't worry, you're fine. It's going to be okay. We're finding g, and h is -3. So what will we do first? We could do a half divided by -3, but in this case, I think it's probably easier to multiply -3 on both sides times -3. I haven't been writing intermediate steps on this particular video, but I think I will on this one. So that'd be 30 plus 24, so -54. Feel like checking that on the calculator. Let me pull up my calculator. So double check. 18 times 3 equals 54. Look at that. We did it. Equals 1/2 g. How do we get rid of fractions? We multiply by the reciprocal because that's dividing fractions, right? So times 2 times 2. You could write 2 over 1, same thing, right? Easy peasy. So 2 times 54 is going to be negative. I'm going to write that down before I forget. So it'll be 108. And that's it, y'all. That's all there is to this problem. Again, if you want to solve these with a proportion, that you're totally fine to do that. It's similar amount of work. This might require one more step, maybe, depending. Arguably, doing the proportion on these might be a little bit longer. I don't know. It's kind of 6 1/2 dozen the other. But this is what I've taught you. So go forth and prosper. We'll see you in the next one. Bye-bye.